Hello everyone, this is Dr. Zach. Today in AP Calculus, we're going to transition from the definition of the derivative to finding some shortcuts, which will make our derivatives a whole lot easier. In today's lesson preview, I hope you found all the different places where the function was not continuous first. So you're not continuous at x equals 3, or wait, that's just it. But you are going to be non-differentiable at x equals 3 because of continuity, and at x equals 6 because you have a corner on the graph. The slope on the left does not equal the slope on the right. If you look very carefully, I'd be worried about this point because it may be possible that you have a vertical tangent line near x equals 1. Now it's time to try to find some shortcuts and transition from the definition of the derivative to some other rule. If we're looking at f of x equals x squared, when you substitute using your definition of the derivative, notice what happens. You've done this problem enough times that when you multiply it out, you should come up with 2x. Now when you were working with x to the 1/2, once you were finished with the substitution and simplifying, you ended up with 1 over 2x to the 1/2 power. Another way to see that is 1/2 x to the negative 1/2. And then from your work with derivatives and multiplying out x plus h quantity squared, you figured out that you come up with the derivative 3x squared. Lastly, when you looked at x to the negative 2, that was the same thing as finding the derivative of 1 over x squared, and you came up with negative 2 over x to the third. If we rewrite that, that would be negative 2x to the negative 3. So as you look at your patterns, what I'm hoping you see is that the exponent went down by 1 for each one of these problems. So the derivative is 1 power smaller than the 4 sample problems we have at the start. So there are beautiful patterns that are happening here. The pattern that we're looking at right now is called the power rule. The power rule says if you find a derivative of some x to the n, now n can be a fraction or it can be a counting number, then what will happen is you drop the n in front and multiply by x to the n minus 1. So for example, if I'm looking for the derivative of x to the 5th power, you could rewrite that the derivative equals, drop the 5 in front, x to the 5 minus 1, which is 4. Now think about multiplying x to the 5th out using your binomial expansion. That's a lot of work. So the power rule is going to make our work a lot simpler. Now, there are some exceptions. If I were to follow the power rule for x to the 0 power, I would say 0 times x to the 0 minus 1. Now, that is just 0. But let's look at this again. If I think of x to the 0 as the constant number 1, because anything to the 0 power is 1, think about your line for a moment. If we were to graph y equals 1, what is the slope of the horizontal line 1? And it is going to be 0. Well, what if we were to do that for any horizontal line? The derivative of any constant or horizontal line is actually 0. So we have a power rule that works with any exponent, x to the 4th, x to the 5th, x to the negative 1/2, and it also works for any constant. The derivative constant is 0. Now, if you want to look at your proof, we would take f of x minus f of a over x minus a and look at the limit as x approaches a. So what you should notice is that you can factor your x to the n minus a to the n, and you're left with, using the binomial expansion theorem, this lovely x to the n minus 1 times plus a x to the n minus 2, and it goes on and on until you get to a to raised to the n minus 1. Now, if we were then to substitute x goes to a for each one of our functions, notice what's happening here. All of these values are going to be multiplied out, and when you're finished, you would be left with n times x to the n minus 1. Now we're going to take these power rules and the derivative of a constant and apply them to some new functions. As we look at our examples, what I need you to remember is that the only two rules we know right now would be that the derivative of your constant is going to be equal to 0, and the derivative with respect to x of x to the n is n times x to the n minus 1. So those are the only two things that we can do. If I'm looking at question 1, the directions say determine dy dx. The derivative of y with respect to x is going to be equal to. Now it's time to apply that power rule. Notice I have x to the 5th power. Well, drop the 5 in front. You're left with x to the 5 minus 1, which is 4, minus, oh no. So the natural log of 3 is not in the list of things we know. So we need to add that. So far we have 2 items in the list. Our third item, the derivative with respect to x of the natural log of x is equal to 1 over the argument x. Okay, so now we're going to take this rule and apply it. The 3 will stay in front of the problem, and then the derivative of the natural log of x is 1 over x. So there you have your derivative with respect to x of our original function. Now, we want to find the instantaneous rate of change at x equals 1. So that just means, of course, find the derivative. We're going to write that dy dx at x equals 1. We're going to substitute the value of 1 in, and we're left with 5 minus 3, or 2. So the instantaneous rate of change at x equals 1 is 2. So for example 2, notice we have a complication. Do you see the multiplication in the problem? We will have to multiply that out so that we can apply our rule to our problem. If we don't multiply it out, none of the 3 rules that we know are going to apply. So when we multiply this out, you will end up with y equals, notice I'm using the variable y because I'm doing algebra, 1 plus your 4x to the negative 1. I'm going to rewrite it so that it's in the form of x to a power plus, and then you'll have 2x squared plus 8x. So I've rewritten the problem, got rid of the multiplication. Now we'll find a derivative. Y prime equals the derivative of the constant is 0 plus, hold on, we're going to take negative 1, multiply it by the 4 because we're dropping the negative and 1 in front. So that's negative 4. X to the negative 1 minus 1 is negative 2. Plus 2 times 2 is 4. Then we're going to have our x plus, now the derivative of 8x is just 8. And here's why. You have x to the 1. 1 times 8 is 8. You get x to the 0, but x to the 0 is the number 1. So when you simplify your problem, you have negative 4 over x squared plus 4x plus 8. And you might be asking yourself, should I find a common denominator? You should not worry about common denominators unless we have some reason to apply the derivative. So for now, what we have is perfect. So the second part of the question, find dy dx when, so this little line here, we're going to represent with the word when, x equals 2. So looking for y prime at 2. Notice I'm doing substitution using function notation. I have negative 4 over 2 squared is 4 plus 4 times 2 is 8 plus another 8, and I get 15. So y prime at 2 equals 15. When you write your work, be certain to be exact. Write y when it's necessary, y prime, and then y prime at a certain value. All right, looking at example 3. Did you notice it is a binomial squared? And that, of course, is not applicable to our rules. So we want to multiply this out. And when you multiply it out, you come up with x to the 4th plus 6x squared plus 9. Now, my equal signs are following. The reason they follow is because all I've done is algebra. The directions say determine f prime of x. Since that's my next move, I write f prime of x. Drop the 4 in front. Here's my x. 4 minus 1 is 3. Plus, drop the 2 in front. There's my 12. X to the first power. And then don't forget, the derivative of a constant is 0. So that part of the problem is done. Ooh, the next part says write the equation of the tangent line at x equals 0. So I want you to remember, the slope of your tangent line is the derivative at a point. So I need f prime at 0. I didn't write it out yet, so let's find it. F prime at 0 is going to be equal to 0. Well, that's highly odd, but that's okay. Y minus y1 equals your m times x minus x1. Now we're ready to substitute. The y value is the same thing as asking for f at 0. And f at 0 is 3 squared or 9. So I have y minus 9 equals the slope at 0, which is 0, times x minus 0, or y equals 9. So the tangent line is horizontal, and it is at y equals 9. All right, so let's look at the next problem. I'm giving you multiple representations for asking for a derivative. When you see the symbols d, dx, that means find a derivative with respect to x. And you should know that it is possible to find a derivative with respect to other variables. Most of the time today, though, we are looking for with respect to x. To make our problem look like our pattern, we're going to write 7x to the negative 4 before we begin. Then I want you to remember one of the rules that we talked about in a previous lesson was the derivative of the sine of x. The derivative of the sine is the positive cosine. So that needs to be in the list of things you know. Just like the derivative of the cosine is equal to the negative sine. And that will come up at some point. So let's see here. What is the derivative of sine? We just talked about that. The derivative of sine is the cosine. So we get negative 2 multiplied by the derivative, which is cosine x. And in the next part, we're going to take negative 4 times 7, negative 28, x to the negative 5. Notice we go straight for the equal sign because the symbol d dx says the derivative of the function, and you just assigned the answer. Example 4 is getting a little silly. 3 little tick marks. That means find the third derivative. So find the third derivative. Find the derivative 3 times. Oh my goodness. So let's first do algebra. Rewrite this as 1/2 x to the negative 1/5 power. Y prime equals 1/2, and the derivative is going to be negative 1/5 x to the negative 6/5. All right, that's the derivative. Well, the second derivative, I suppose we should clean this up. It's negative 1 over 10. Here's your x to the negative 6/5. Second derivative now, negative 1 over 10 times negative 6 over 5, x to the negative 11/5, because I'm subtracting 1 each time. So that's my second derivative. So I hope you left some room to find that third derivative. What we simplify, we get y equals 6 over 50, and 6 over 50 reduces to 3 over 25 times x to the negative 11/5. All right, so y triple prime is the next one we're looking for. Y triple prime equals negative 33 over 125 x to the negative 16/5. So when you see triple prime, I'm looking for the third derivative. And now, look at this one. This is another symbol. What this tells us is we want the second derivative of what's inside. Okay, so, and our sixth rule of the day, d dx of e to the x is e to the x. Now, if we find the derivative of the inside, but need one more, we write d dx. The derivative of 3e to the x is just 3 e to the x. The derivative of the cosine, negative sine of x. Now, you should have that in your mind at this point. We need the derivative again. So the derivative again is going to be equal to 3e to the x. The derivative sine is cosine. So we have 3e to the x minus cosine x, and we are done with example 5. The lesson practice is in your book. So on page 114, I've chosen several questions that I think are very interesting. So give these a try. Only work for 25 minutes, and then we'll continue with the lesson. So hit pause now. I chose 3 questions to discuss with you. Number 44. The reason I chose this one is some people have a bit of a challenge with monomial division. So if you're dividing by a monomial, just split the problem into 2 parts before you find the derivative. So the algebra is where people have a little bit of trouble with that one. Number 46 is very similar. Number 52, playing with your negative exponents. So just double check that you got a negative 2/3, x to the negative 4/3 minus 3 sine of x. And 54, what I want you to be on the lookout for this one, make certain that your slope of a tangent line is actually a number, not a variable expression, but a number. It has to be a number. Now that you've practiced working with 6 of your basic functions, let's put it all together. The derivative, it is the slope of the curve at a point. It's also the slope of your tangent line. And another name is the instantaneous rate of change. The limit definition, so that would be what this is called, your limit definition, will lead you to a derivative. You are expected to know the limit definition and how to apply it. So on the first day of class, you also worked with velocity. Velocity can be represented by v of t, and it is actually the derivative of position. So position in math class is generally called s of t, and the derivative of position is your velocity. Average rate of change is the slope of the secant line. And what you also know is that it is the change in distance divided by time. It's also called your average velocity. You can use your slope formulas to find it from way back when you took Algebra 1. They're just finding slope for your average rate of change. Now it's time to think about some ideas from physics. And I wanted to go over basic concepts so that when you read the question, you can apply your mathematical ideas. When a ball hits the ground, that means that the height of the ball is considered 0. If the ball goes up and then comes back down, let's draw that. Ball goes up, ball comes back down. The velocity at the highest point, which is your derivative, is 0. And the reason for that is that your slope is 0 at the highest point. Your initial height is called s naught. Your initial velocity is called v naught. When you measure acceleration is just a fancy way to say gravity. We'll call that a of t. So acceleration with respect to t is going to be negative 32 feet per second squared if you are using the English system, and it's going to be negative 9.8 meters per second squared if you are using the metric system. Speed is the absolute value of your velocity. Now, the reason it's absolute value is because it's telling you how fast something is moving, but not the direction. So speed is absolute value of velocity. You have 2 formulas related to height to use in the physics problem set. The first one is used for the metric system, and the second one is used for the English system. The English system uses the 32 feet per second squared as the acceleration, and that's why it's negative 16 for your a value. And if you were to look at 9.8, cut it in half, you get your negative 4.9. That's why the metric system is using the height function is listed first. Couple things to remember. Your position function is usually s of t. If you take the derivative of your position, you're going to get velocity. If you take the second derivative of position, or v prime of t, you get acceleration. So they are all interconnected. So for example 6, we're told that the initial velocity of a toy rocket is 10 meters per second. The initial height of the toy rocket is 2.5 meters. We're going to write a height equation for the path of the rocket. In order to do that, recognize that you're using the metric system. So S of t is going to be equal to your metric, which is 9.8 divided by 2, t squared plus some initial velocity, v naught t, plus s naught. Now from there, let's substitute. We know that s of t, which is the position function, must equal 4.9 t squared. The initial velocity is 10, so we have plus 10t, and the initial height is 2.5. All right, so we've written our function, and now it is time to think about when will the rocket hit the ground. So when you hit the ground, that means that your height is 0. So all we need to do is set 0 equal to 4.9 t squared plus 10t plus 2.5. So now we're going to use the graphing calculator. Let y1 equal your function. Figure out where the function equals 0. Use the zeros for that. T equals 2.266 seconds. Now, I gave you the answer, but you really need to practice. Make certain that you know how to use the calculator. Question C, what is the velocity of the rocket when it hits the ground? So that's asking for velocity. Well, S prime of t is equal to the velocity. And the velocity equation, go back up to here, find the derivative, is going to be 9.8 t plus 10. Specifically, I want to know the velocity when we hit the ground. So v at 2.266 equals what number when it hits the ground? And figure it out, write it down. Now, the units that you're going to be working in will be meters per second. The next question, what is the speed of the rocket 1 second before it hits the ground? So I'm looking for the speed, which is the absolute value of your velocity, and I want it 1 second before it hit the ground, so that's 1.266, and that answer is going to be a positive value, and that positive value should be 2.407 meters per second, because speed is positive. So let's take a close look at example 8. The rock is dropped this time from a height of 100 feet. That gives you two pieces of information. The first piece of information that you must know is that the velocity at 0 is equal to 0. This means comes from the dropped rock. Also, S at 0 is equal to 100. And that's because it says it was the initial height. But you were also given the S of t is equal to your negative 16t squared plus 100. So in this problem, you did not have to write your equation. Question A is find the average velocity. Now, average velocity is going to be measured in feet per second. So this is a slope of a secant line for average velocity. So that will be S at 2 minus S at 1 over 2 minus 1. When you substitute your 2 into your function, you get negative 16 times 4 plus 100 minus your 16 times 1 plus 100, all divided by 1. And you end up with negative 48 meters per second. Since your velocity is negative, the ball is falling downward. Find the velocity of the rock when t equals 2. So this is your instantaneous rate of change. And when you're looking for the instantaneous rate of change, that's a derivative. So s prime at t is equal to your velocity, but the derivative of the function we have is negative 32t. And when you substitute your 2 in, the instantaneous rate of change is negative 64 feet per second. Let's go back up here and fix this. This should be feet per second for question A. Now for C, at what time is the velocity of the ball equal to 0? So if you take the velocity equation that you wrote, v at t equals negative 32t, and you set it equal to 0, you know that in this problem, t equals 0 seconds. So today's lesson provides a lot for you to practice, and notation matters. So I'll be looking for that. Work on lined paper so that you're able to keep everything nice and neat, and make certain your questions are numbered so that they're easy for me to check over. You have a fabulous day.